It was started. So whoever's going to start listening to that, it's me saying, okay, that started. Okay. Right, so this is chapter 5, stability. What do you know about stability already? What does it mean if something's unstable? I can't hear you. Errors. If it's stable. Yes, yeah, that's right. If I start explaining what an unstable scheme is, an unstable scheme is no use, essentially. What an unstable scheme means is the errors that accumulate in your numerical method tend to dominate. The errors tend to dominate, and your solution soon sort of diverges off to infinity. So an important thing of any numerical method is to ensure we've got a stable method. And there are some cases where a method will be stable and some where it will be unstable. So we're going to be looking today at stability of Runge-Kutta methods. Okay, so this is on chapter 5. So essentially, derive stability functions. I'll mention what they are in a minute. Plot the region of absolute stability and determine whether a Runge-Kutta method is what we call astable. Okay, so when I get onto astability, there are quite a few different types of stability, and there's quite a few different criteria. I'm just going to refer to two. One is absolute stability, and the other is astability. So there are things like L stability, weakly stable, etc. I'm just going to refer to absolute stability and astability. Okay, unfortunately, having a look at when we look at stability, it will depend upon whatever ODE we're solving. So there's no general way of actually saying, is this method going to be stable for this ODE? So what we tend to do is we tend to compare our methods against what we call a model problem. And the model problem is a very simple first order ordinary differential equation. So here you've got first order lambda times y. So first order derivative of y equals lambda times y. Lambda is some number, okay? It's just anything. So that's a very, very simple ODE. That's what we're going to be using to determine our stability regions and where methods are stable or not. This is quite easy to see. This has the exact solution of y equals exponential function of lambda times our independent variable t. Okay, so we know what the solution is. We know how the solution behaves. We need our numerical methods to actually behave like that solution. Okay, if we let a variable z equals our step length h times lambda, what this means is our solution should converge when z is negative. Okay, so if instead of lambda, let's say we have a positive number, t is going to be positive, so t is a range 0 going up. Exponential function where t is positive and lambda is positive, that's just going to go off to infinity. So as t gets higher and higher and higher, the exponential function is going to diverge off to infinity. That's no use to us. We want something that goes down to 0. This is a model problem. Okay, we want a model problem to behave so it will go to 0. So what we say is we're going to be looking at the values when this thing in the bracket is going to be negative. Okay, so the exponential function of a negative value is going to tend towards 0. So as more and more negative you get, the closer and closer y should get to 0. So we're only interested really in the left-hand plane. By plane, I mean we're looking at the complex plane. So we're going to be looking at the real numbers on the horizontal axis, and we've got imaginary numbers at the vertical axis. Okay. If we let z equals a step length h times lambda, for a single step of length h, we multiply our exact solution by the exponential value of z. Now this is very useful. This means we can have a look at our numerical method we want it to behave like the exponential function of z. Okay, so what we do is when we look at the explicit stability for Runge-Kutta methods, we want our what we call a stability function to behave like this function here. Okay, this is a model problem. This is what we want. What we get might not be what we want, but that's stability. Okay, for an equivalent step of length h, our approximate solution is multiplied by some function of z. So we want this function of z to resemble the exponential function. So that's what we do. We're comparing it against this exponential function. And if it does behave like the exponential function, we can say that our scheme is stable. Okay, so at all times we're using the model problem. The model problem has the solution of an exponential function. We want our numerical method to also behave like that exponential function. So this is where we come to the idea of a stability function. Okay, if we're just looking at single step methods, okay, a single step method can be written in this form. So yn plus 1, that's our next solution at step length h away. So we know what yn is, that's our current solution. Yn plus 1 is our next solution, step length h away. Well, we can write that in this form. So yn is our current solution, and that's multiplied by some function. Rz is just a function of z. And remember, z is just h times lambda when we apply to the model problem. So we can think of this Rz as being an amplification of yn. So yn times some function will give me our next value. Okay. So this Rz will tell us whether a scheme is stable or not. Okay, how Rz behaves tells us whether a scheme will be stable. And Rz is what we call a stability function. So in order to determine whether a scheme is stable, we need to derive Rz. Okay, I mentioned I'm going to be looking at two types of stability. The first one is region of absolute stability. You may have heard Lida mention this. Essentially, we want the modulus of our Rz function to be always less than 1, or less than or equal to 1. Well, if I'm going to go back a slide now, okay, if Rz is greater than 1, what this means is y is just going to diverge. Because we're keeping multiplying y by a number greater than 1, it's going to get bigger and bigger and bigger, and eventually it's just going to get too big, it's going to diverge to infinity. If Rz is less than 1 or equal to 1, y will converge. It will converge, eventually, hopefully, it will converge to 0 and it will behave like the exponential function. So that's why we want Rz to be less. Okay. So this leads on to the definition of the region of absolute stability. And it's given in set notation. Z is some complex number. Okay. If the modulus of Rz is less than or equal to 1, we have the region of absolute stability. So for all z for which this is true, that means z is in absolute stability region. So for example, here's just a sketch. So I have a complex plane. I have my real number 9 on the horizontal axis. I have my imaginary number line on the vertical axis. Remember, we're only bothered with the left-hand plane because that's the only side that our model solution converges for. And if your z is anywhere within this region, it's stable. Okay, you can say your method is stable. Rz will be different for all your methods. So the Euler method will have an Rz function. Trapezoidal method will have an Rz function. The second order Runge-Kutta will have another one. So depending on what your method, you'll have a different function Rz. Okay, so the region of absolute stability is where Rz, or the modulus, is less than 1. Okay, so the simplest single-step method is Euler method. So I'm going to now derive our stability function for the Euler method. So just to remind you, Euler method is current value of y plus step length h times whatever your function of t and y is. So remember, t and y is the right-hand side of our first order differential equation. So our function is just lambda y. So I have yn plus h lambda yn. Now remember, z is equal to h lambda. Okay, so then I could just factorize out yn to give me 1 plus z. So the Euler method for our model equation is simply 1 plus z times yn. That 1 plus z, that is my stability function. So Rz is equal to 1 plus z. So therefore, the region of region of absolute stability is the modulus of 1 plus z is less than or equal to 1. Remember, z is a complex number. It has real parts, it has imaginary parts. Okay, so the modulus of a complex number is the real number part squared plus the complex number part squared, add them together, square root, that's your modulus. In other words, it's Pythagoras applied to the real and imaginary parts. Okay, so what this means is if I was to graph the region of absolute stability for the Euler method, we have this region here. Okay, so for example, let's say that my z was minus 1 on the real number line and 0 on the imaginary number line. That would coincide to this part here, and therefore we would have it stable. If I had z over here, let's say z was minus 3, this is outside the region of stability, so therefore it would be unstable. Okay, so that's my region of absolute stability. Rz, or the modulus of Rz, has to be less than or equal to 1. Okay, so I've got this graph in your notes, top of page 59. Very simple model equation. So instead of lambda y, I've got minus 2.3 y. Okay, so my initial value problem is y dash equals minus 2.3 y. I'm going to use Euler method with step length 1 and step length 0.7. Okay, when h is 1, okay, my z will be minus 2.3. Minus 2.3 is about here, where my mouse cursor is. That's outside the region of absolute stability. When h is 0.7, I'll have 0.7 times 2.3, which will be somewhere inside here. Okay. So with h is equal to 0.7, I'm in the region of absolute stability. And this blue line is the Euler solution. And as you can see, as t gets higher and higher, my solution tends to 0. Okay, so it oscillates a bit about positive and negative values. But the point being, if I was to carry t on to infinity, my computed solution would tend to 0. But I do the same graph, but this time with h is equal to 1. Okay, if h is equal to 1, my z value is minus 2.3. That's outside the stability region. So you can see here, this red line is the same method using the step length 1. And as you can see, it's oscillating out and it's going to diverge. So the red line is unstable solution. The blue line is a stable solution. Okay, so that's essentially what we're going to be doing. We want to derive that stability function but for our Runge-Kutta methods. Okay. Right, to do so, we make a couple of assumptions. Okay, one assumption we make is we're going to look at a single step of a Runge-Kutta method. Okay, so we're not going to be bothered with our C values. Okay, the stuff I presented on page 59, that takes a while. Well, it took me a while to actually get it sort of sorted in my head. What I'd recommend you do is there's a very good explanation on this in Butcher's book, 2008. if you are sort of wanting a bit more sort of clarification, check out alternate sources. Okay, so in other words, I'm not really going to assess you on any of this stuff. This is kind of background. It's like when I was doing the bivariate Taylor series. That's where things come from. You won't be assessed on this. So hopefully you won't worry too much about it. Okay, so if you look at the K stages of an S-stage Runge-Kutta method, we're only doing one step, and I'm ignoring the C terms for now. What we have is in the second part of the f of ty. Okay, so this is all in the second part of f of ty for each stage. We have y0 is the current value of y plus a11 times whatever k1 is plus a12 times whatever k2 is, etc., etc. So this is for an implicit scheme. Okay, so I've presented it in this way because what we can do is I'm going to define a vector y, or big Y. Now, big Y is just all of my k stage values. Okay, so big Y is a vector of k stage values. So in other words, the left-hand side of this system here. Okay. I'm also, this is a bit of a cheat, this is a bit of a fudge, but I'm going to define a vector which I've called 1. You notice it's in bold. This is a vector, and it's simply a column vector of 1s. The reason we've done this is it makes the presentation so much simpler. Okay, so 1, or my vector 1 is simply a column vector of 1s. My big Y is a column vector of my k values. Okay, so what we can do for the model problem, okay, we have my vector of 1s times y0, so that's this term, or these terms down here, plus h lambda, okay, that's my f value, so that's the k1, k2, etc., times a, so you can see all the a11, a12, etc., times big Y again. Okay, so remember big Y, the k1, k2, etc. Okay, so this is a matrix representation of this. Okay. If you're a bit confused about that, drop the mic, not in the cool sort of rapper sense, but I could drop it if you want. Yeah. Okay. Sorry, where was I? Yeah. So if you want to sort of think where this comes from, it will be a lot of algebra. Well, what you can do is write out this in full for, let's say, for a 4-term Runge-Kutta method. Write out in full, deconstruct it, and then reconstruct it in this form. Okay, so I've gone straight from there's the system to the matrix representation. Okay, so I've missed a kind of, there may be a bit of disconnect between that stage and that stage. Okay, but if you want to sort of check that out for yourself, grab a few pieces of paper and a cup of tea and try it for yourself. Should take you about an hour. Okay, so in short, what I mean is, what we then have is, well, if h lambda is z, I have my stage values y is equal to my vector of 1s times y0 plus z times the A matrix times my vector of stage values. So this is an implicit relationship. Y depends upon whatever y is. Okay, so if I subtract z, a, y from both sides, and then I factorize in terms of y, and then invert and take back over the other side, I get this term. Okay, so this is y is my stage values, I is the identity matrix, z is h lambda, a is whatever comes from my Runge-Kutta method. That is inverted. This is a square matrix. If I invert that, multiply it by my vector of 1s times my y0, I have my k stage values. Okay, so if we substitute in the expression the yn plus 1, y1, which is my one-step solution, is equal to the current step plus z times my b values. So remember, b values are multiplied by the k1, k2, k3. Okay, so in the fourth order Runge-Kutta method, which you should be very familiar with by now, b is a sixth, a third, and a sixth. Okay, so this b, okay, b is a column vector of your b values, but it's transposed. So that then becomes a row vector times your k, times your stage values. Okay, well, from here, y is this matrix inverted times 1, y0. So instead of this y here, I replace it by this, and we have that. Okay. If I factorize y0s out, I've got 1 times y0 plus all of this times y0. So what that means is for a Runge-Kutta method, and this is the sort of thing you should highlight in your notes, for a Runge-Kutta method, this is our stability function. I'm not going to ask you to derive that. Don't worry about it. This is where it comes from, but you'll be given this in an exam. Okay. It's kind of like the order terms for Runge-Kutta methods. I'm not going to ask you to derive them. It's nice to know where they come from, but they will be given to you. Okay. This is for a general Runge-Kutta method. Doesn't matter whether it's implicit or explicit. What we're now going to do is we're going to look at how we calculate the actual function Rz for explicit methods, and then we're going to look at implicit methods. It's actually very easy. Okay, for explicit methods, there is something called the geometric series of matrices. Okay, this is going back to linear algebra stuff. If you don't know what geometric series of matrices are, check out the preliminary chapter at the beginning of the notes. There's a section deriving this. Okay, I'm not going to talk about it too much. In other words, if we have a square matrix T, the identity matrix minus T inverted, we can write that as the sum of T raised to some power K. So that would be T0, which is the identity matrix, T to the power 1, plus T to the power 2, plus T to the power 3, etc. Okay, this is what we call the geometric series of matrices. So we're going to use that. Instead of the I minus ZA inverted, we can write I plus ZA plus Z squared A squared plus Z cubed A cubed, etc., etc. So that's just using this summation, this series sum, in the place of y minus I minus ZA. Okay. Then we can substitute this order condition in. Essentially, what this means is instead of the one vector of ones, I can replace that vector of ones by my C vector. Now, the C vector just comes from your left-hand side of your butcher tableau. That comes from your finite difference. That comes from your Runge-Kutta method. But in doing so, we reduce the power of A by 1. So I think in the notes, top of page 60, essentially it comes from an order condition, but essentially all it means is where you got B transpose A to the power K times the vector of ones, you replace that with B transpose A to the K minus 1 times the vector of C's. Okay, so what we have is there's my, by the way, all this is only for an explicit method. So we have this geometric series of matrices. If I expand out this bracket here, I'm going to get Z B transpose times I, the identity matrix, plus Z squared B transpose times A times the vector of 1, plus Z cubed times B transpose times A squared times vector of 1s, etc., etc. Apply that order condition here. Essentially, you subtract 1 from the power of A and replace the vector of 1s by your C vector. Okay, this is the stability function for an explicit Runge-Kutta method. What we want to do is we want to compare it to the exponential function. Okay, exponential function, if you expand out the series, Maclaurin series or Taylor series, the exponential function, you have this pattern. So in other words, it's z to the power p over p factorial. So this is our series expansion for your exponential function. We want the Rz to behave like this exponential function. And what we can also say is the order of our method, our Runge-Kutta method, is the highest value of p these two agree to. Okay, so look, you got 1 in the first term, you got 1 in that term. Okay, if z b transpose times the vector of 1s is equal to z, you got first order. If z squared b transpose a to the 0 times c, that equals a half, you got second order, and so on and so forth. Okay, so that's how we determine the stability function for an explicit method. It's dead easy. Oh dear, I've gone way back. Okay, I'll show you how easy it is. Okay, here's an example. I've got a explicit Runge-Kutta method here. It's got 4 stages. Doesn't mean it's 4th order. Okay, just because there's 4 stages, doesn't necessarily mean it's 4th order. Okay, so this is my method, written in iterative form. Okay, so if I convert this to the vector matrix A, vectors B and C. Okay, so the A's are what we multiply by K1, K2, etc. here. Your C's are what you multiply H by, and your B's are what you multiply the K1, K2 by in order to get your Y. Okay, so hopefully you know where to get the A, the B, and the C from. MATLAB. Okay, actually I might as well, we've got a MATLAB open. Might as well show you how to do it. Is that big enough? Fonts. Okay. It's literally 30 seconds in MATLAB and you could do this question. Is that big enough? Yeah. Okay, so what do we got? We've got our A. So I type in my A matrix. Okay, so they're my A matrix. With the B and C, we always assume that they're column vectors. Okay, and finally my C vector. Oh, should be column. Okay, so I've typed in my A, my B, and my C. Okay, what we now need to do is we've got to check. We go up in order of P and see if everything agrees. So I'm just going to go back to the, where's my slides? There we are. Okay, so the first one I have is B transpose times C. So B transpose times C equals 1/2. Okay, in the notes you might notice, but I use rats. Now rats will just convert the 1/2 into the rational fraction. So B transpose times C is 1/2. That coincides with the exponential function. So next I do is B transpose times A to the power 0 times C. Oh, sorry, that was that one. And next thing I do is I raise the A to the power 1, 3/16. And then I do A to the power 2, 1/48. Okay, so my function will be 1 plus Z plus 1/2 Z squared plus 3/16 Z cubed plus 1/48 Z to the power 4. If I try and go higher, I try and go A to the power 3, let's get 0, A to the 4, 0, A to the 5, 0, etc. So basically, you do that a few times until you get it, and you use your last non-zero value. Okay. So that's what I did here. Okay, so this is the coefficient of z squared. That's the coefficient of z cubed. That's the coefficient of z4. What I wanted was this. I wanted a half, a sixth, a 24th. What I got was a half, something else, and something else. Okay, so this is our stability function for this for our method. This is the exponential function expanded. These agree up until the second order term. Anything higher, they don't agree. So this method is a second order method. Even though it's four stages, it's only a second order method. And if you plot the region of absolute stability, this is the plot you get. Okay, that's very easy to do in MATLAB. I'll show you how you do that now. Okay, if you want to plot the region of absolute stability, the first thing you need to do is have an array of z values. So I'm going to say -5 to set of 0.1 to 1. I'm going to do the same in the y direction. Okay, I'll just explain what I'm doing here. X is going to be my real number part. Y is going to be my imaginary number part. So I'm going to go for real numbers from -5 to 1, imaginary numbers -5 to +5. Okay, so then I'm going to make a grid of X and Y values. What that does is that, well, I'll show you what it does. There you are. Ooh, maybe a bit too, font's a bit too large to show you. It just makes a grid of X and Y values. So that, I'll show you what that command was. It was mesh grid. So it puts X and Y into an array. Makes it easy to do surf commands and contour commands. Now I put them together, I combine them. X plus 1i times y, that makes z a complex number. Okay, so that's my real part. The x is my real part. I times y is my complex part. Notice it's 1i. I don't know why, but it seems to sort of get a bit tangled up if you don't put the 1 in front of the I. Okay. So Z is now a matrix of complex numbers. Okay. So what was my so the stability function was 1 plus Z plus a half Z plus 3/16 times Z. Oh, Z squared. Notice it's dot to the power before the power. That's 1/48 times z to the power 4. That's your stability function. Okay. What I'm going to do now with a 2-minute create a surface plot. Oh. The reason I balls up a bit there is I didn't do the absolute value of z. Okay, remember, modulus, we want the modulus of our complex number z. Okay, so absolute value of z. I'm surfing that against the real number part and the imaginary number part. And it shouldn't have taken that long to do that. Sorry? Ah, Z, yeah, sorry. Well spotted. I should have used R, and I've broken the computer. you what the surface looks like. For the region of absolute stability, we only need to know the values where the surface equals 1. Okay, so you'll have some sort of bowl shape, and if you take a slice where the height of that surface is 1, you'll get a circular or a region. Okay, so this is contour of x and y, absolute value of r. This 1, 1, 1. If you do that, and I've done it for all the Runge-Kutta methods, that's what you get. Yes.